Welcome back, everybody. Let's work through this group work on line integrals and vector fields. First problem has us computing this line integral where C is a line segment from this point to this point. As always, our first task is to get our parameterization for our curve. And so since this is a line segment, thinking way back to section 12.5, our classic way of parameterizing a line is with our starting point plus all scalings of our direction vector. And so here we can pick one of these to be our starting point. Maybe I'll choose it to be this first point. And we want to stretch along this line segment to our second point, which means that our direction vector would be the difference between the two. And so 1 minus -1 gives us 2. Then 6 minus 5 gives us 1, and 4 minus 0 gives us 4. This gives us the change in x, y, and z between these 2 points. And so feeding that in, we have our starting point plus all scalings of this direction vector. And if we write that out in the different components, it's -1 plus 2t, then 5 plus t, and 4t. That's our parameterization. And we now have everything we need to translate and compute our integral. All right, so our integral is going to translate as the integral from a to b, which is going to be the parameter values that start us at our first point and end us at our second point. The t value that's going to start us at our first point is t equals 0, and then t equals 1 is going to stretch us and stop at our second point. So our integral is going to be from 0 to 1. And x and z we are going to plug in from our parameterization. So our x is -1 plus 2t minus z squared. And then our ds differential, this is the magnitude of our derivative dt. And so here for our parameterization, we just need to compute this thing's derivative. So that's going to be, because of the linearity, just the constants 2, 1, and 4. And so taking the magnitude gives us root 4 plus 1 plus 16, just squaring those up. And so it's root 21. So that's what gets multiplied against all of this stuff. It's that root 21 dt. And we can now take that root 21 and toss it out front, integrating from 0 to 1 of -1 plus 2t minus 16t squared dt. And so anti-differentiating now, we get -t plus t squared minus 16 thirds t cubed, evaluated from 0 to 1. And if we plug in 1, subtract what we get when we plug in 0, we will get down to -16 thirds times root 21 as our final answer. It is, in case you were wondering, close to -24.4-ish. Let's look at the next one. All right, here we have a different curve and a different line integral that we are computing, and we are using a different differential, dx instead of ds, so that'll just change how we translate things. But here, looking at our curve, we have kind of two portions. We have our circle portion and this straight line portion. We'll need to get parameterizations for each, and then this integral is going to break up as the integral over the first piece plus the integral over the second. And so we'll just compute those individually, and then we'll just add them up. All right. For our first curve, this is part of a circle, so I think polar coordinates is a nice way to go about getting our parameterization. And so our parameterization is handing us our x, y points. And if we're using polar, x is r cosine theta, y is r sine theta. But all along this circle, our radius is 2. And so we have 2 cosine theta, 2 sine theta as our function. And in order to start where we want to start and end where we want to stop, we want to start our parameter theta at 0 and move it up to pi over 2 and stop there. So theta from 0 up to pi over 2. So let's start there. And our integral here then is going to translate to the integral from 0 to pi over 2. X is 2 cosine theta, y is 2 sine theta, and our dx differential, right? We're looking at our x from our parameterization, and we are taking its derivative. So this becomes x prime dt, where our particular t is theta, since that's our parameter. And so x prime over here is going to be 2, the derivative of cosine is negative sine, so negative 2 sine theta. And so we will have a negative 2 sine theta d theta for translating our differential. All right, so collecting all of our constants, we have a negative 8 out front. We have sine squared times cosine. And so we can do a quick u sub if we wanted to. We could also just kind of just by hand feel this out. Antiderivative is going to have to involve sine cubed of theta. The derivative there would be 3 sine squared times cosine. We like the cosine, we like the sine squared, we don't like the 3, so we need to divide that out. And we still have the negative 8 out front. Again, you could do a u sub with u equals sine here, and you'd get to the same place eventually. Weight from 0 to pi over 2. If we plug in pi over 2 to sine, that's going to give us 1. So this gives us 1 cubed. Plug in 0 to sine, we get 0. And so at the end of the day, this just hands us negative 8/3 for the value of our integral over our circular portion here. For our line segment, we have a parameterization similar to our first problem above. Since it's a line segment, we'll use our line parameterization. We're starting now at the top point, 0, 2, and marching down to our point, negative 1, 1. And our direction vector will then be negative 1, negative 1. So we have our starting point plus all scalings of our direction vector, negative 1, negative 1, which gives us the function negative t 2 minus t. And again, t starting at 0, stopping at 1 will move us from our beginning point 0, 2 to our end point negative 1, 1, as we want. So from this, we can translate our second integral. So it's going to become the integral from 0 to 1, where x is negative t, y is 2 minus t, and again, our dx becomes x prime dt, where if x is negative t, And for us, x prime is just the constant -1. So we have a -1 getting multiplied in there. That'll cancel off with the negative on the t, and so distributing our positive t, we get 2t minus t squared. And we can anti-differentiate, get t squared minus t cubed over 3, evaluate from 0 to 1. And that's going to give us 1 minus a third minus 0 minus 0, which is 2/3. And so at the end of the day, taking our negative 8/3, and adding the 2/3 gives us negative 6/3, which is -2 for our final answer. Next one. Now we are considering vector fields and line integrals over vector fields. Here we have pictured this blue vector field, and we have two curves that we're thinking about integrating along. And so we are wondering whether these line integrals are going to be positive, negative, or 0 based on what we see. And so let's talk about it. Well, if we're integrating along this first curve, the key observation here, since what each of these line integrals is really adding up, are the tangential components of our vector field vectors. In order to figure out whether this is positive, negative, or 0, we're wondering how these vectors are moving with us or against us. And here, as we move from the right to the left, these blue vectors are all moving in the direction of our motion. And so we're going to have positive tangential components, and that integral should be positive for the first one. Positive, since our f vectors are pointed in our direction of motion. And now for our second curve over C2, we're moving in this direction. Now notice our vector field vectors are coming out, it looks to be orthogonal to our curve here. And so as we move in this direction, the tangential components are all going to be 0. We're just going to be adding up 0 all the way through, because these are all orthogonal to our direction of motion. And so because we're just adding up 0 the whole way through, our second integral here is going to be 0, since our f vectors are orthogonal to our direction of motion. All right, next one, we have an actual computation that we're doing here. So we have another vector field line integral, where this is our vector field, cosine x, xy, and we have a particular curve defined by this equation, running from the point at the origin to -8, 2. So, as always, first step here to compute our line integral is to get our parameterization of our curve. And so, we're dealing with points in the plane, so our parameterization is going to hand us the xy points. And our curve is actually defined by equation where x is solved for in terms of y. And so here we can get our parameterization very quickly just by plugging in for x at -2y squared. And here using y as our parameter. So our parameter t is y. And in order to start at the origin and stop at -8, 2, well, with y as our parameter, we can just read it off from the y. And so our y is moving from 0 up to 2. So with that, we have our parameterization. We have everything we need to compute this integral. And so here, translating this becomes the integral from 0 to 2 our vector field is the cosine x, xy, and if we want, we can plug in now from our parameterization based on what x and y are. So here, cosine x becomes cosine of negative 2y squared, and xy becomes a negative 2y squared times y. And so there's our F vector field, and we're dotting that with our differential dr, and the dr differential comes r prime dt, where r prime is the derivative of our parameterization with respect to our parameter. So here, r prime, taking the derivative with respect to y, gives us negative 4y, 1. Right, that's coming from the derivative of our parameterization here. And so that's what gets plopped in right here. R prime is negative 4y, 1. Now we just take the dot product here. So we're going to get, I'll put the cosine times the negative 4y, I'll put the negative 4y out front, negative 4y cosine of negative 2y squared, and then plus this negative 2y cubed times 1, and so minus 2y cubed dt. And with that, kind of the dot product dust has settled, and we can now simply integrate to compute this thing. Over on the left, this would be a u sub computation. We could absolutely do a u sub with u equals negative 2y squared. The derivative of that is actually negative 4y exactly. So this would be very clean. We could also just kind of do it by hand with that observation. The antiderivative has to be sine of negative 2y squared. And the antiderivative of the second piece is going to be y to the fourth over 2 once we do 2 divided by 4. And so we're evaluating this from 0 to 2. And this gives us sine of negative 8 minus 16 over 2, which is 8, and then minus 0 minus 0 once we plug in 0. So our final answer is the not so pretty, but nice and exact, sine of negative 8 minus 8. One last problem. Here we have a few different vector fields. We're wanting to match them up with their formulas up above. And so this first one, no matter what xyz point we're looking at, we are always attaching the same vector. So we're looking for a picture where all the vectors look the exact same, just kind of shifted to be attached to a different point. These vectors are all moving around. These vectors are all pointing different directions. These ones are swaying. But over here on the right, all of these vectors look like just copy-paste images of each other. They're all pointing in the same direction. And so that's going to be D for this first one. Sorry. The second one, now the x and y components are always 1 and 2, but the z changes. And so that means as this is positive z values, this vector should be pointing up. If this thing has negative z, we should be pointing down. And so as we look at these different pictures, this picture, they're all pointing up, so that's not it. This one has up and down, so does this one, but B is pointing different x and y directions as we move around, whereas our x and y's are always the same. And so that looks more like A. For this third one, z is always 3, no matter what. So always pointed up, but x and y could be pointing different directions. And so that feels, well, out of these two remaining, right, this B has vectors that point down as well as up, so it can't be that. And in fact, C is the one. Those are all pointing in the upward direction for z, and x and y look like they're changing. And so process of elimination, this last guy has to be b, but why is that? X, y, and z, so whatever our point is, that's the direction that it's pointing. So kind of a 3D picture here is, if that's our point, x, y, z, then, well, the vector x, y, z points to it, but we just are kind of thinking about that vector now being attached to that point. And so, depending on where that point is, it's just going to be kind of continuing this line coming out of the origin. So that looks like B. All these vectors look like a big explosion is happening out of the origin. That's it for today. Great work, everyone. I'll see you next time.